Okay, welcome everybody. Today we're going to have a lecture from Ricardo Stuardo. He's at Universidad de Oviedo. He's a postdoc there, and he will speak about aspects of the twisted circle compactification of SUSY theories and the holographic dual. So, Ricardo, all yours.
Well, first of all, thank you very much for the invitation. It's always very nice to speak among friends. And I apologize because of the long title. I've always been against these type of things, but sadly, twisted circle compactification is the whole name of the thing, so there was no other option. And I think the way in which this talk is organized is such that we will decompose what these things mean. Like we're going to discuss what is the twisted circle compactification. We're going to talk about holography, as you can guess from the title, but there is a field theory section and there is a gravity section, so we're going to cover both parts. And it's mostly going to be based in this paper that I published last year with Prem Kumar, who is a professor in Swansea. But also I will mention these other two works that I did with Carlos Núñez and Marcelo Yarzo that were naturally led up to this other paper. And then in the end, I'm going to briefly mention this kind of generalization or like a more mathematical description of the system in this paper that I did with Neil McPherson and Paul Meriting. So the outline of the talk is the following. First, we're going to start with a very brief motivation about field theories on a circle, just to discuss what the problem is or what is the thing that we want to tackle. Then we're going to go to the most classical holographic example, which is n=4 super Yang-Mills. We're going to first tackle the field theory part, and then we're going to look at the holographic description. Finally, I'm going to mention like different generalizations that you can have, and then I'm going to end with like a summary and things to look up in the future. And if at some point you feel like asking a question, please do. Don't get mad about those things. So when you formulate a QFT in this case, we're going to focus on Minkowski 3 times a circle. You need to impose boundary conditions for the fields on the circle. Generally, you impose periodic boundary conditions for the bosonic fields, but for fermions, you have the freedom of imposing periodic or anti-periodic boundary conditions. And this has a very important effect. This is basically choosing what the spin group is in the S1, but I'll just mention that as a side comment. So the idea is that if you impose anti-periodic boundary conditions, you see here we have a 4-dimensional Lagrangian for a Weyl fermion, lambda, and this exponential of n+1/2 makes it anti-periodic. And the point is that once you reduce on the circle, each of the modes of the fermions has a mass. You inherit this mass term. And you see that very interestingly, there is no massless mode. So the n=0 or the n=-1, the least amount of mass that you can have is 1/2 or -1/2. So the point is that when you impose anti-periodic boundary conditions, you don't have a zero mode. This is very important because when you have a supersymmetric field theory, when you impose periodic boundary conditions for bosons, they will have integer modings or integer mass spectrum, whereas the fermions have integer masses. So you see that you completely break the Bose-Fermi degeneracy, and therefore you break supersymmetry, because in supersymmetry you need the bosons and the fermions to have the same mass to be super partners of each other. Then again, if you continue to be in a supersymmetric theory, if the fermions has a massless scalar superpartners, there is a one loop correction that gives mass to this scalar, and at very low energies, lower than the size of the circle, what the field theory that you get is just pure Yang-Mills in one dimension less after reducing. And as I said in the introduction, I'm going to focus more on maximally supersymmetric Yang-Mills in 4 dimensions. So this is the field theory part, but how do you see that supersymmetry is broken by antiperiodic boundary conditions on the gravity side? So the point is that here you need to realize the compactification of the circle along as you vary the energy, which is in the ADS-CFT is the radial direction. And the holographic dual to the compactification of the circle is this deformation of ADS5 plus S5. You see that if f is 1, you recover pure ADS. But this function f has a 0, and at that point in the 0 of f, the coordinate phi shrinks to 0, and this resembles the compactification of the field theory circle. So throughout this talk, I would refer to these coordinates when they are like multiplied by this harmonic factor here. I would refer to them as field theory coordinates because basically they are kind of, when asymptotically, the field theory coordinates. The point is that in order to study supersymmetry on the gravity side, you need to look at the Killing spinors. For this, you have to solve a spinorial equation that I will mention how you get it later. But the point is that in general, for this geometry that I showed before, for mu different from 0, already this equation has no solutions. But let us do something interesting to see what's the consequence of imposing anti-periodic boundary conditions. So asymptotically, the geometry looks like pure ADS5 plus S5, but with one of the Poincare coordinates of the ADS identified. So let's solve the Killing spinor on pure ADS5 plus S5 and impose anti-periodic boundary conditions along this circle. For this, we only need to look at the spinor on ADS5, which takes this form. So let me go to the next slide. I put it again. So you see that this first part that is proportional to epsilon minus, which is a constant spinor, it would depend linearly on phi. And if we want to impose anti-periodic boundary conditions, because it's linear, it doesn't satisfy anti-periodicity. So you have to set epsilon minus equal to 0. The similar thing is for this other contribution of the spinor. Because it's constant, again, it cannot be anti-periodic. So therefore, choosing anti-periodic boundary conditions also kills the Killing spinor on the gravity side. And this is the counterpart of the breaking of the Bose-Fermi degeneracy in the field theory. So the question that we wanted to address is whether it's possible to impose anti-periodic boundary conditions for the fermions and retain some amount of supersymmetry in the process. If possible, what is the effective theory in 3D? And what is the holographic dual of this operation that you are doing on the field theory? And the answer that we found is that you need to introduce a background gauge field for the R-symmetry. I'm going to mention what these things are in the next slide, to compensate for the anti-periodicity of the fermions. So this concludes the introduction. And if there are no questions, I will proceed with the field theory part.
Ricardo, so the
Yes.
main idea is a thermal theory to make a thermal theory supersymmetrics, maybe the motivation.
Well, it's not really thermal because you are doing nothing to the time direction.
No,
You are
no,
not-
but in the sense that when you do thermal, you apply anti-periodic
Yeah. So it's similar, but it's not the same because it's not a thermal theory, because you're just putting the theory instead of on like R4 with a circle, you are putting it on Minkowski 3 and a circle. So there is no notion of Euclidean time.
Okay. So it's different.
Yeah.
Okay.
It's different. Yeah. And actually, there is, well, maybe I can comment on this later. So let us start with a toy model before going to the n equal 4 case. Let's start with the n equal 1 vector multiplet, n equal 1 super Yang-Mills, which is just Yang-Mills and a Weyl fermion. So when we compactify this theory on a circle, we need to, again, impose boundary conditions. We're choosing, again, periodic for the bosons, anti-periodic for the fermions. As before, the fermion will get a mass. And when you reduce, well, you will get an extra scalar of the component of the gauge field along the circle. But it will get massive because of the Yukawa interactions. So it's the same thing as before. We see that it breaks supersymmetry. However, n equal 1 super Yang-Mills has a U1 R-symmetry, which is a global symmetry, which basically you can think of as just changing the fermion for a phase. You do a phase transformation of the fermion. And so we're going to introduce a background gauge field for this symmetry, which is basically just putting like a background. In the same way you put a background electric field on a fermion, it works in the exact same way. You just, what do? You modify the derivative to introduce a covariant derivative. So we modify the gauge covariant derivative to a new derivative, which is the gauge plus the background gauge field, which, very importantly, we're going to take it to be constant and to only have components along the circle. This is going to be very important because then when you study the mass spectrum of the fermion, you see that this parameter Q of the background gauge field enters in the mass spectrum. So naturally, you can say, oh, this is a thing that I can tune myself. So I can tune it to be precisely the thing that it's bothering me, and I will recover Bose Fermi degeneracy. And this is something that you can do. However, n=1 super Yang-Mills has the U1 R-symmetry is anomalous. So when you do these phase rotations of the fermion, you introduce a theta term, which is something that we don't like for this talk. But this is just a classical example to see how the mechanism works. And we are now going to move to a theory which this symmetry is not anomalous, so everything in the procedure works really, really well. So if this example is clear, let us move to n=4 super Yang-Mills. I'm not going to show the Lagrangian, but I'm going to tell you what it has. So it has a gauge field, has 4 fermions, and 6 real scalars. And we're going to take them, all of them, to be of the gauge group, in the joint of the gauge group, which is SUN. This theory, again, has an R-symmetry, which in this case is SO6. And the vectors, the scalars, are 6 of them, so they transform in the 6 representation, which is the vector representation of SO6. And the fermions transform as spinors of SO6, which is the same thing as the fundamental of SU4, because SU4 and SO6 are basically the same thing. But we are going to work with SO6 then the entire time. So SO6 has 3 SO2 subgroups. So you can think of it in the vector representation. It's a 6x6 matrix. You can take 3 independent 2x2 blocks. This is the 3 SO2 subgroups. And we're going to pick a basis such that this rotation rotates just a pair of scalars. What do I mean by this? Is that if I do one of these SO2 rotations, I just rotate the scalar 1 with the scalar 2. So in this case, it's natural to take this complex combination of the 6 scalars, and then each SO2 or U1 acts independently on each of these complex scalars. Then, just for convenience, it's very natural to pack everything into this vector, which has the complex scalar and its conjugate, the other scalar and its conjugate, and so on. And the way in which these U1s act, it's given by these matrices here. So the first one gives you how it acts on the scalars. So you see that if I do a rotation, the scalar, a U1, which is just a phase, the complex scalar will rotate with plus the phase, and the conjugate will rotate with minus the phase. And because the fermions also transform, I need to tell you how the fermions transform, and basically they also transform by a phase, but the phase is given by 1/2. And this is how the fermion 1 transforms, the fermion 2 transforms, and so on. I hope that this is clear. Then what we're going to do is, again, the same thing as we did for n=1 super Yang-Mills. We take the theory on a circle, we put antiperiodic for the fermions. But now we see that from the n=1 example, we couple the theory to a background gauge field for a U1 symmetry. So you can ask myself now, Ricardo, you have 3 U1s. Which of them are you going to take? Well, I'm going to take a diagonal combination of the 3 U1s, which is basically I'm going to take the 3 U1s and I'm going to use the same parameter for all of them. This which is what I've called U1 diagonal. And again, the background gauge field is just a constant, and it only has components along the circle. This is the generator of this diagonal U1. So you see that it's what you expect from before. You just add them all up because it's just a sum of the 3. And you see that there is one fermion which transforms differently from the rest. And this is going to be very important. Why? Because when you study how the mass spectrum of the fermions transform when you include this background gauge field, you see that the fermion number 4 will have a different contribution from the background gauge field. And more importantly, notice that the bosons, the scalars, they also get a shift on their mass spectrum because of the inclusion of the background gauge field. Why is this important? Well, we can take the fermion number 4 and say, okay, I knew what to do before. I'm going to tune this parameter Q to cancel this annoying part and make this fermion periodic again. When you do that, the mass spectrum, or the KK modes, which is what they actually are, of the fermion get shifted and they get aligned with the KK modes of the gauge field. On the other hand, you see that for this same value of Q that we chose before, the scalars and the leftover fermions, they align, but they don't align, again, the KK modes, the masses of the KK modes, they align, but they don't align neither on integer or half integer modings. They align on these fractions of 3, if you want. And it's very interesting that the n mode of the fermion aligns with the n-1 mode of the boson. But then again, you see that you recover the Bose-Fermi degeneracy even though it's not at the integer or half integer moding. And you can say, okay, Ricardo, you recover Bose-Fermi degeneracy, but this is not enough to have supersymmetry, because I can cook a theory which, with 1,000 bosons, 1,000 fermions, they have the same mass, but it's not necessarily SUSY. And this is a precise comment, but this thing that we are doing can be recast as in the following way. So you can define these new fields, eta as this phase times the fermion number 4, other fermions, eta A, and a new set of complex scalars. So when you define super Yang-Mills, n equal 4 super Yang-Mills, but using these fields, when based on the previous ones, they have a new set of boundary conditions, which is this fermion eta has periodic boundary conditions, but the new fermions, the other fermions, and the scalar, they have this weird boundary condition where you need to go around the circle 3 times to go back to yourself. And very interestingly, this set of boundary conditions split naturally the n equal 4 multiplet into an n equal 1 vector and 3 n equal 1 chirals. Well, this is, you can always do this even if you don't impose these weird boundary conditions. This is a decomposition that you can always make, but it's somehow showing you that this deformation that we're doing preserves n equal 1 supersymmetry of the total n equal 4 that you start with. And you can see that it actually preserves supersymmetry by studying a supersymmetry variation of the action. And the only relevant term is this boundary term. And you see that with the boundary conditions that we're imposing, this thing is precisely 0. So that signals that supersymmetry is preserved. And for example, if instead you want to impose anti-periodic boundary conditions without this addition of the background gauge field, this boundary term will not be 0, and it will tell you that supersymmetry is not preserved, which is what you expect, because when you put anti-periodic boundary conditions without this extra background gauge field, you break the Bose-Fermi degeneracy. So, okay, what do we have so far? We have, in the 3D theory, we have a theory that preserves 4 supercharges and has a massless vector multiplet, because this has a 0 mode, basically. And we have a tower of 3 massive chiral multiplets. So the 6 real scalars are massive, and the leftover 3 fermions are also massive. It's very important to say that these scalars, they parameterize the Coulomb branch of the n equal 4 theory. But now, because they are massive, the Coulomb branch is completely lifted. So this is something that we're going to see as well from holography. However, from the reduction of the gauge field, we will get a new scalar, which indeed can take BEVs, and it will parameterize a one-dimensional Coulomb branch. But for what we're going to discuss, we're not going to break the gauge symmetry. Oh, if I'm going too fast, please tell me. Well, so we have this theory that has a massless field and a set of massive KK modes. So as I said before, when you are at an energy scale which is lower than the radius of 1 over the radius of the circle, you need to integrate out all of these massive fields. This is what we are going to do now. The thing is that in 3 dimensions, when you integrate out a fermion, you create a Chern-Simons term in this way. So if you had a Chern-Simons level, when you integrate out one fermion in the adjoint, it's shifted by this amount. But okay, so we need to take care of this. But remember that the mass spectrum of the fermions that we have is not symmetric with respect to n equals 0, should be. But so you could say, but Ricardo, okay, it didn't depend on the mass, it depends on the sign of the mass. So if you have one positive, you also have one negative, they should cancel out. So in the end, there should be no contribution. But as shown in this paper by Kasani and Komargotsky, you need to regularize this sum because you are summing over all the infinite n modes, and you need to do a regularization. And in the end, the regularization spits out that the Chern-Simons level that you are generating is precisely n, the same n as the rank of the gauge group. So the resulting theory in 3 dimensions is n equal to SUN level n, which is a gap theory. And this is also something that we're going to see from holography. Because you have a Chern-Simons term, now the Chern-Simons term acts like a mass term for the gauge field. So now you also lift the Coulomb branch of the scalar, of the extra scalar that you have by reducing the gauge field. And there would be there are going to be new vacuums due to this phenomena. So one observable that we're going to compute later is a Wilson loop that grabs this circle that we are compactifying. And without going into a lot of details, you need to compute this thing here. And the point is that when you are in this vacuum that we're studying, the expectation value of this theta is 0. So this exponential is just 1. So the expectation value of this loop is not 0. And this is going to be important, that is not 0. And this will signal the breaking of the center symmetry of the gauge group.
Ricardo, sorry,
Yes.
maybe it's a silly question, but are you in the large N approximation or
no,
no?
not yet. No.
This
is just a field theory. It's a classical field theory computation. Well, not this one of the loop, but not yet. I haven't taken large N at any point.
So what is the
but
0
when,
then?
Okay, when you want to compute, yes, sorry.
And so in that 0 and that theta, what is? There's a trivial vacuum.
Because in the trivial, yeah. Because you remember this theta is the gauge field that you get by reducing on the circle, and we were studying the theory near the vacuum where theta is 0, has 0 Bev.
Okay.
Yeah.
Thank you.
Yeah, but I haven't taken, well, obviously when you want to compare with the holographic computations, you need to take the large N limit. Okay, so this is the end of the field theory part. So if there are any questions about this, please ask them now. I don't know if it's clear how the mechanism works. If not, if there are no questions, I will continue. So because we're studying a deformation of n equal 4 super Yang-Mills, naturally, we should find a deformation of ADS5 plus S5 that has the two features that we want. First of all, it has to have a shrinking circle. So at some point, there has to be a S1 that shrinks to 0. And the other feature that we want is that it preserves 4 supercharges. And for what we're going to do next, it's convenient to use the following parameterization of the 5 sphere, which is given by this. So this parameterization makes manifest the 3 independent U1 subgroups of the SO6 symmetry, which is the same symmetries that we were interested in in the field theory. So this background is obtained by lifting a solution that was found by Andres Anabalon and Simon Ross a couple of years ago. And it looks like this. So you can say, Ricardo, this part here looks exactly the same as the thing you showed before and broke SUSY. I'll say, yes, it looks exactly the same up to two things. First of all, the F is different, has a different power. And second of all, you see that there is a vibration of the phi sphere over the field theory circle. And this is the thing that will allow you to preserve supersymmetry. Let's completely ignore the flux, the phi flux, and let's talk about the geometry. So here you could say, oh, where are all these powers coming from? I will tell you later. But notice that when R goes to infinity, F goes to 1. This function theta, this contribution goes to 1, but this factor here remains. And this is going to be important because this is exactly what allows you to preserve supersymmetry. This is something that you have to keep in mind. So first of all, why have I chosen this weird parameterization? Why didn't I just call this R0 or something? Well, in order for the circle to shrink smoothly, you need to impose that when you look near the tip, it has to look like R2, like two-dimensional flat space in polar coordinates, and to fix the periodicity of the circle. And when you do this, you precisely find that the parameter Q that you introduce that controls where the circle shrinks, it's related to the radius of the circle in this way, which is exactly what we found in field theory that allowed you to preserve supersymmetry. Moreover, as I said before, when you look really far away, when R goes to infinity, the metric is almost ADS5 crosses 5, except for the vibration, this constant part of the zeta function. And when you take care of the coefficients precisely, it looks like there is a gauge field, a background gauge field, that fibers the U1 subgroups of the sphere. And if you notice, this is precisely exactly the same background gauge field that we use to preserve supersymmetry. And it's actually acting on the 3 U1 subgroups, and it's the same for the 3 of them. So this is exactly the same as we did in the field theory part. So that's why we chose these parameters before. So now, how is supersymmetry preserved on the gravity side? Well, you need to look at the supersymmetry variations and impose that the variations of the fermion fields are 0. In type 2b, when you only have F5 flux, it leads you to this equation for the SUSY parameter epsilon. And basically, when you have spaces of this form, you can decompose it into an ADS5 part, an S5 part, and, well, this piece is just because you need to complete the dimensions of the spinor in 10D, and because you are in type 2b, you want the spinor to be chiral, so this is why you add this extra bit. So before, remember that we found that the spinor on the ADS was this, and the spinor on the S5 is just this. This for pure ADS5 crosses 5, again, you take the product, and as we saw in the introduction, without the background gauge field, when you impose anti-periodic boundary conditions, you completely break supersymmetry. So now we're going to see how the inclusion of this background gauge field, or this constant vibration part, allow you to preserve supersymmetry. Basically, you just need to look at the geometry asymptotically, and you see that it's very easy to convince yourself that you can obtain the spinor of the fiber sphere if you do this replacement in the previous spinor. And you will have two different contributions. One will have this exponential, this power in the exponential, and the other one will have this. But since Q is related to the radius of the circle as 1/3 of the radius, only this one here will be preserved when imposing anti-periodic boundary conditions on the circle. I don't know if I made myself clear. Like this piece will now respect the boundary conditions that you are imposing. So in the end, the spinor just looks like this. And basically, when you count how many there are 4 of them, because this guy has 4 independent components. And you say, oh, but this is the spinor asymptotically. What happens with the spinor in the full background? Well, you just need to do this replacement and find what epsilon plus is, but basically it's in any case it's going to give you 4 supercharges. So it's the inclusion of this constant part of the vibration, which is exactly the same gauge field that we used before, that allows you to preserve supersymmetry in the geometry, because now this spinor is indeed antiperiodic. Yeah, are there any questions? Well, I feel like I'm going a bit fast, but if you can tell me to go slower.
No, Ricardo,
Yes.
there is a interpretation of why these floods solve the problem for the supersymmetry. You're
This
adding this vibration to the S5.
Yeah, this one.
This is like a flux, right? Because you have put in the vibration there.
Yeah,
Modifying the
it would
S5.
be like a flux if you reduce to 5D, probably. If you reduce on the sphere, it behaves like a flux.
But why is this solving the problem for the supersymmetry?
Well, it's from the mathematical point of view, it's because it makes now the spinor antiperiodic.
No, yeah, but
yeah.
Okay. I mean, it works, but I don't
Yes.
understand why it works, because it's like this is like adding an additional term in the supergravity in 10 dimensions. So what's the interpretation? What's the physical interpretation of this?
Well, it's adding. Well, it's indeed adding something in 10D because you are changing the 10D metric.
Yeah.
And well, the interpretation is that you are changing the. Well, you're changing the. Yeah, it sounds a bit weird because it's the same thing that I said, but you are changing the boundary conditions. No, it's okay. It is. You are changing the boundary conditions for the metric at infinity. So such that it doesn't look like ADS, but it looks like ADS plus this thing. And the interpretation of this thing that you are adding is the gauge field that you introduced in field theory. I don't know if that answers the.
Maybe it's a bit like the snake eating its own tail.
Yeah. See. I don't think I have a deeply mathematical answer for this question.
Okay, but if you look at the 10-dimensional theory, what did you add there?
Well, I added nothing. It's the same fields. It's just a deformation of the metric. You see that I haven't added any extra matter content to the theory. It's still the metric and the flux, the same flux that you had in ADS5 plus S5.
The problem is that the compactification is different because you are adding this vibration there.
Yeah, the compactification is different, and the interpretation is that if you reduce on the sphere, instead of having just pure metric, you have the metric and a gauge field in 5D.
Okay.
And the interpretation of this gauge field is the thing that it's like going on a circle. No, it's the gauge field that you're adding is the same gauge field of the field theory.
Yeah. Okay. Thank you.
Yeah, but you are doing if the question was if I was adding some extra matter content to 10 dimensions, this is not the case.
Okay. Yeah.
But you start from the 10-dimensional supersymmetric theory, right? And so when you go to phi, that's where you lose the supersymmetry. I don't understand.
Yeah,
I got a bit lost with these dimensions.
Yeah. So in 10D, pure ADS5 cross S5 preserves 32 supercharges. It preserves 16 Poincaré and 16 superconformal supercharges. Okay. The way to see that in 10 dimensions is you solve, well, for ADS5 cross S5, you solve this spinorial equation called the killing spinor equation. Okay. The problem is that an equation is not just, you need boundary conditions for this equation. And if you impose anti-periodic boundary conditions on one of these fields on the S1 that you have, it completely kills the spinor. So there is no supersymmetry. And what we are showing us is that by adding this extra vibration, you can preserve some of these 32 supercharges. You cannot preserve only 4 of them.
Okay, but isn't like when you do a Kaluza-Klein compactification, uh, you have more when you go to lower dimension, right? It appears some gauge fields that looks like okay, that they are need, but they are actually the isometries of the space in higher dimension. It's like
Yes,
okay,
yes.
when you go to lower dimension, that gauge field are actually the killings that came from the higher theory. So my question is, you there's it's not like an interpretation from the higher supersymmetry theory in 10 dimension that when you go to lower, okay, you that supersymmetric charge that you have now they transform like something like difference or it's nothing, not good.
Yeah, so
Uh,
it's related because if you reduce on the S5, what you will
mm,
find is a 5-dimensional theory that has the 5D metric and a gauge field, which is precisely this gauge field that you have here.
okay.
And this gauge field, normally, when you reduce, as you said, when you reduce on a manifold, for example, if in pure DS5 process 5, you reduce on DS5, you will land on a 5-dimensional theory, which it's a gauge supergravity, and it has an SO6 symmetry because the sphere, which is the manifold in which you reduced, has an SO6 symmetry.
Mm-hmm.
What you can then do is take truncations. You can say, oh, I'm going to consider just a subgroup of SO6, and that gets rid of a lot of fields. So you can say, okay, I want to truncate the SO6 theory down to a U1 theory. You can do that, and you land precisely on metric and just a gauge field, which is precisely this gauge field. And that gauge
Mm-hmm.
field has the interpretation of being it's related to the R-symmetry group of the dual theory. So basically here it's
Okay.
telling you that you are introducing a gauge field for the R-symmetry, which is precisely what we covered in the field theory section, that you said, oh, this theory has an SO6 R-symmetry, but I'm going to introduce or gauge, but it's not gauge because it has no dynamics, but we're going to gauge the IU1 subgroup of this R-symmetry.
Okay. Okay.
I don't
Better.
know if this answered the question. If it doesn't, we can discuss it later.
No, much better. I'm trying to follow. So thank you, Ricardo.
Okay, no problem. So now I want to discuss some features of this thing. So the way in which supersymmetry is preserved is very similar in which this thing we call supersymmetric solitons because that's the name that they were given in the literature. It's very similar to a topological twist, as this is something that we explained with Carlos and Marcelo in one of our previous papers. Basically, the idea is that there is a mix or a twist between the R-symmetry, which in our case is the U1R or the U1 subgroup of the SO6 symmetry of the sphere, with the spin structure of the circle, which is basically, in this case, the boundary conditions. So there is a mix between a global symmetry, which is the R-symmetry, and another global symmetry, which is the Poincaré symmetry along the circle. There is a mix of these two, and they compensate to preserve some amount of supersymmetry. And this same thing can be done for higher dimensional manifolds, and these things are called topological twists. This is the thing. And again, so the point of the R-dependent part of the vibration is that the space ends smoothly at R equals 0. But I think the highlight is that the behavior, the way in which supersymmetry is preserved, is very similar to a topological twist, hence the name twisted circle compactification, because it's a twist in the sense of the topological twist. So I said before that we were going to look at these Polyakov loops and how to compute this in holography. Well, you take a string worksheet that wraps the radial coordinate and the S1 that is shrinking, and you evaluate the on-shell action. And the point is that this action is finite, hence the Polyakov loop has a non-zero expectation value, which is what we expected from the vacuum that we were looking at. So hence we find that, again, from holography, we match this field theory computation, saying that the center symmetry is broken. And so now we match, we can say, oh, we have these two things that are the same, so we can match this 10-dimensional configuration, which we can say that it's dual to the SUN level n field theory that we found before. Moreover, you can put this is, I'm just going to briefly comment on this. You can study, in holography, you can study the Coulomb branch of the field theory, but putting proof branes on the geometry. Basically, you say, ADS5 process 5 is constructed out of the 3 branes, placed in some position. You say, oh, I'm going to put a brane away from them, but a proof such that it doesn't deform the geometry. And if this brane is free to move, you say, oh, this is this freedom is parameterizing the Coulomb branch of the theory, of the dual theory. The idea is that you play the same game that you did in ADS5 process 5, but now in this deformation, and you find that there is no freedom. All the branes want to go to the tip of the cigar. All the branes want to go to the same point. So because there is no freedom of moving the branes, you find that the Coulomb branch is lifted, which is exactly what we found in field theory, because the scalars were massive, and so they could not have a Coulomb branch. So this finishes the ADS5 process 5 or the n=4 super Yang-Mills part. If there are no questions, I will go with the generalizations. But it's going to be the same features all over again. So don't worry if there's not going to be a lot of new ingredients.
Ricardo, you talked about the twisting.
Yes.
But when you twist, you usually change the superalgebra, right?
Wait. So this is not the twist in the sense. Are you thinking about like Checker-Schwarz or something like that?
Yeah.
It's not the same. It's just a coincidence of the name. I've had this discussion with supergravity people. It's not the same thing. It's just the name coincides.
And what do you call it, twist?
Because it's very similar to this topological twist, which is a thing introduced by Witten gazillion years ago.
Okay.
Because twist is the sense that there is a mix between the R-symmetry and the global symmetry of the space-time.
Okay.
Yeah, it's not that. It's not Checker-Schwarz. It's not that. Yeah, it's I realized later when I started talking with more like supergravity people, they were saying, "Oh, why are you calling it twisted circle? If there is, how do you twist a circle?" And then we realized that we were talking about different things.
Okay.
So I'm going to. So if you remember from the introduction, I said that the only key ingredient was supersymmetry. So conformality is not needed. The conformal symmetry of n=4 super Yang-Mills is not a key ingredient in this construction. So then let me generalize what I said before to maximally supersymmetric Yang-Mills in different dimensions, so more than 4, and then you don't have conformality, but you still have holographic duals of these theories. So we're going to consider backgrounds constructed out of DP branes for odd P. So I apologize for there are going to be a lot of numbers here. But basically the idea is that when you have maximally or an odd DP brane is a field theory in even dimensions. For example, the D3 brane, the theory is a 4-dimensional theory. So when you have a maximally supersymmetric Yang-Mills in even dimensions, the R-symmetry is an SO and it's even as well. For example, n=4 super Yang-Mills in 4D has SO6. Maximal supersymmetric Yang-Mills in 6 dimensions has SO4, and in 2 dimensions is SO8. So it's always even. Hence, you can always do this decomposition that we did before. You take the even dimensional matrix and you decompose it in 2-dimensional blocks. And the rank is going to be given by this. And the point is that you can play exactly the same game. You say, okay, I have these 2x2 blocks. I take a combination in which I do the same transformation for all of them. And you play exactly the same game. And the idea is that the holographic dual looks like this. I know it looks pretty ugly, but let's look at the ingredients and you will see that it's exactly the same. First of all, you have the field theory directions and you have another function f. And the function f shrinks to 0 at some point. So again, you have that a circle shrinks to 0 at some point. Then you have, it's not written in the same way, but there is the holographic coordinate here that has 1 over f, which is exactly the same as before. And this is a sphere is a odd dimensional sphere. It's exactly the same as before. For example, if you put p equals 3, you recover the phi sphere. And you see that, again, we are choosing this parametrization where all the U1 subgroups of the sphere are manifest, and we are gauging all of them with the same gauge field, which again has the form of 1 over r and a constant that doesn't vanish at infinity. Don't worry about the parameters. Think about it, that it has the same features, has something that doesn't vanish at infinity, and this is what will allow you to preserve SUSY. So I just want to comment on this and say that just one example, Carlos, Marcelo, and I look, for example, at the holographic dual of the D5 brane, so P equals 5, and you have a 3 sphere. And we computed a bunch of observables, for example, Wilson loops, Toft loops. We had some notion of how to compute the gauge coupling holographically. We looked at the entanglement entropy. We computed the density of state. And we looked at spin 2 blue balls. And all of them tell you that the field theory is confining, which is exactly what you expect from a theory in which holographic dual in which some of the directions shrink to 0 size. It would be very interesting to do the field theory analysis. So the same thing that we did for n equal 4 super Yang-Mills, which it was not large n, it was a classical computation. So you can do it for a maximally supersymmetric Yang-Mills in 6D. And it would be very interesting to see what happens when you integrate out the adjoint fermions. Remember that when we went to 4 to 3D, it generated a Chern-Simons term. So it would be very interesting to see what is the counterpart of that thing, but from when you go from 6 to 5. This is something very interesting. And for example, this is some plots of the Wilson loop that we computed. You see that when the separation between the quark and the I-type quark increases, the energy goes linear. So this is the behavior of a confining theory. What is interesting, though, is that there is a minimum separation. You cannot put the quark and I-type quark as together as you want. There is a minimum separation, but this is a feature of the D5 brane because the UV of the theory is not well defined. You need to S-dualize, you need to do some stringy operation to define the UV, and basically that is what this minimum distance is signaling. So you say, okay, and what happens now for the even DP brane? So maximally supersymmetric Yang-Mills in odd dimensions. Well, here there is a problem because now the R-symmetry is going to be SO and an odd number, which it doesn't have the same decomposition as before. So it would be a bunch of SO2s, but there would be one that you cannot do anything with it. So what this means is that it would mean is that one of the scalars, because we're looking at the vector representation of the R-symmetry, would not be charged under the diagonal U1. So basically it means that we need to be a bit more careful when doing all of this procedure. And there is also some evidence of the gravity side that this would be a bit more iffy to look at. So basically the idea is that as following the question of, who asked me? Lucas, I think. So you reduce on the sphere, you get a gauge supergravity, which is SO something odd in this case. And you say, oh, can I truncate to the SO7, for example, down to a U1? The answer is yes, but you cannot truncate it to an Einstein-Maxwell sector. You always get an extra scalar, and basically the point is that you cannot put this scalar consistently to 0. Because of its equation of motion would be something like this. And if you put the scalar to 0, well, the potential is in the minimum. And then this basically imposes that the Maxwell field also should be 0. So you cannot put this extra field to 0. So again, the gravity side, as in the same way as the field theory side was telling you there is something weird about this, the gravity side is also telling you that there is something not going well. So something else that we have been not talking about is that I've been only discussing maximally supersymmetric cases. So you can say, oh, Ricardo, does it work for things that are not maximally supersymmetric? And I will say, of course. There are all of these duals to four-dimensional theories, which are conformal and supersymmetric, but with different amount of supersymmetry. So for example, ADS5 cross T11, it's a one field theory. ADS5 cross YPQ is another field theory. There are all of these different backgrounds that have different amount of supersymmetry or different R-symmetry. And basically how to do this procedure, or just on the gravity part, it was done by, well, Carlos and people at Swansea, so Dimitris, Ali, and Peter. And they basically did exactly the same that we did before and computed a lot of observables in all of these backgrounds with the twisted circle compactification. So it is possible to do it even when you don't have maximal supersymmetry. And as I said before, you don't even also need conformality. So you can have theories which are not maximally SUSY and not necessarily conformal. So for example, our first paper on this thing with Carlos and Marcelo, we looked at a theory that had these symmetries, which is not an ADS, and it has two different SO R-symmetry groups. And what we found is that it was the first hint to some diagonal combination. We found that if you put a gauge field for the U1 of this R-symmetry and the U1 of this other R-symmetry, to preserve SUSY, they need to be the same. Yeah, so I just want to comment on that for the case of non-maximal, non-conformal theories. And the last thing that I want to comment is something that I did with Neal McPherson and Paul, which basically is using G structures. And I will not tell you what a G structure is, but I will comment how we obtain the generalization. You can choose another coordinate patch of the sphere. So far we have been using the one where you make all of the U1 subgroups manifest, but you can always, for example, here we take the 5 sphere, you can always parameterize this as a CPN fiber over U1. So this is CPN, this is a U1, this is the fiber over the U1, and this is the gauge field that we were introducing ourselves. And the point is that when you write the metric like this, you can also do complete some squares, such that now you somehow move this gauge field from psi, you move it to phi, the field theory circle. And notice that now the F is not here, it's not in the field theory circle, it's rather on the sphere circle. It might seem silly to do this, but what this does is that it makes manifest that all of this transverse space, it's a Calabi-Yau. And because it's a Calabi-Yau, it preserves an SU3 structure. And you can play the same game for the D1 brane and the D5 brane, and they will preserve an SO4 and an SU2 structure. Basically, the idea is that you rewrite the metric in a different way, and you find that the transfer space has some different properties that you could not see. I mean, they were encoded somehow in the old parameterization, but in this way, you make manifest that this is a different type of, well, you make manifest the structure of the system. So the idea that we have is the following. Okay, so in type 2, supergravity in 10 dimensions, you can consider a background of this form. So Minkowski D and then some internal coordinates. And when you impose that this background is supersymmetric, it imposes some geometric conditions on the internal manifold. This is what this G structure procedure is. I'm not telling you what it is, but it's what it does instead. So a particular case of this is the case when you have, again, the Minkowski D doesn't change, but you take out one direction of this internal space and you make it a circle. And if you notice, this is exactly of the same way, of the same form as what we had before. So we had Minkowski 3, some circle with a gauge field that it's part of the internal manifold, and the rest. And this is of the same form. You have the Minkowski, the circle with a fiber, and the rest. So what we found is that the supersymmetry conditions, when you write the spacetime as this thing, they are exactly the same supersymmetry conditions as the supersymmetry conditions now on Minkowski d+1, but with additional constraints on the field strength of this guy here. So what we managed to map basically is the supersymmetry conditions, or let me say it otherwise, we managed to find let's call it supersymmetry generating technique to find solutions which corresponds to reductions of Minkowski on a circle. So in the end, we found a generalization of, I know this looks ugly, but I will tell you, if you notice it would be exactly of the same form. You have some function of the radial coordinate, the Minkowski that you have and we all love, the circle that shrinks with the same f as before, the radial coordinate with the same f. Now you change the CP2 for any, or the CPN for any Keller-Einstein manifold, and there is, again, a new fiber. The only extra pieces are this function delta, and H that now has an extra piece, which, for example, for the D3 brane, this is the normal piece that we had before, and all of this contribution here is new. Well, new for us, but this thing existed before. So this extra harmonic factor was found by these people, so Benvenuti, Mahato, Leopoldo Sayas, and Tachikawa. And basically, this parameter B controls a web of a meson in the dual field theory. Something very interesting about this is that the geometry, you say, okay, this new harmonic factor looks super ugly. Like, can you do anything with it? And the one interesting feature is that even with this awful contribution, this function delta that I'm not telling you what it is, the geometry is still asymptotically ADS. So you would interpret it as, first of all, you have the compactification, but this other thing basically also breaks conformality. So it's like if you, it also breaks conformality. You are doing two different things, two different operations on the field theory. And we found some other conditions from compactifications from Minkowski 5 to Minkowski 4 and Minkowski 3 to Minkowski 2, which were precisely the cases that I told you that were a bit harder to do. So this is the last slide. If I went a bit too fast on this, I apologize, but this is the time for questions. If not, I will move to the conclusion.
Ricardo, one question.
Yes.
This solution, the one of Leo, etc., still is singular after you do the thing?
Yeah, so exactly. So the solution of Leo has f equal 1, delta equals 1 as well. So it's just the Calabi-Yau. This is a Calabi. So R, the Keller-Einstein, and the circle, they form a Calabi-Yau. And it's still singular. It's this thing that we always discuss about how when you flow from a conformal theory to a non-conformal theory, it always has to be singular in the IR.
But then here you are saving the singularity.
No, sadly no. The singularity is at the same point in which f shrinks to 0. It's at exactly the same point. It's a sad coincidence. Yeah. But what is interesting is that if you look at the geometry close to the end of the space, you find that it looks like if there was a D7 brane smeared over the Keller-Einstein manifold. So the metric looks like some logarithm thing, which is the harmonic factor for the D7.
Yes. Thank you.
Yeah. I will move to the conclusions. So what we did was we looked at 4-dimensional N=4 super Yang-Mills, which gauge group SUN, and we saw that when you impose anti-periodic boundary conditions and introducing the background gauge field, you manage to preserve some amount of supersymmetry, which is N=1. We saw that in one particular vacuum, the gauge theory is N=2 SUN level N. And the level N came from integrating out all of the massive fermions of the chiral multiplets. We also studied the holographic dual, which is this supersymmetric soliton or this deformation of ADS 5 versus 5. And we saw that the way in which supersymmetry is preserved is the same as a twisting procedure. So what things can we do we would like to do? An n equal 1 version of Witten Yang-Mills model, which basically would mean to find these supersymmetric cigar geometries in the D4 brane background now. We would like to apply this technique to resolve singularities of backgrounds that existed beforehand. For example, the abelian Maldacena-Núñez model that has a singularity in the infrared. Also, something that we are doing now is we are doing the field theory analysis of the D1 brane. This well, it works in the same way, except that you have an SO8 R-symmetry group. And something that for sure you can do, guaranteed, but we're not doing, is doing like a 3D n equals 2 version of the Sakai-Sugimoto model. That is, you take this background that I just showed, or the deformation of ABS 5 × S5, and you put probe D7 branes that will act as flavors. So that is what it means, Sakai-Sugimoto model. And that's everything. Thank you. And I don't know what time it is, but hopefully I didn't go over time.
Nah, it's okay. Thank you, Ricardo.
No, I think it was precisely an hour because we started late.
Yeah, no problem. And also
Okay.
we interrupt you a bit. So let me stop the recording and we can continue.